We present Laser, a method to learn latent action spaces for efficient reinforcement learning. The best action space for learning manipulation differs based on the task. In learning continuous control, a good action space offers a simple relationship to the reward function, facilitating convergence. In robotics, these ideas motivate the familiar set of robot controllers. We present Laser to provide a data-driven approach to discovering these action spaces. We propose a decomposition of policy learning. It factorizes the problem of mapping observations to actions in the original action space into two subproblems. First, learning an action space for a task or task family in the form of a mapping F between action spaces. And second, learning another mapping G from observations to actions in the new action space, A bar. This second mapping is in fact a policy in the new action space. While the policy changes between task instances, our hypothesis is that the first mapping remains constant, facilitating training for unseen instances of the task. Laser proposes a solution to the problem of action representation learning in the form of a variational autoencoder model which reconstructs low-level actions from latent actions, along with a latent dynamics model predicting future robot states. We propose two variants of our algorithm, offline and online Laser. In offline learning, we train an RL algorithm to convergence and use it to collect a demonstration dataset. We then train Laser and use the resulting latent action space in subsequent tasks. In online Laser, we interleave policy and representation learning. The latent decoder becomes part of the policy, and we use the actor gradients through the decoder to assist learning. We trained Laser on variants of two different tasks. In Door, the agent must learn to open a door to a fixed angle. In Wipe, the agent learns to wipe a streak of dirt off the table. In our first experiment, we observed that offline Laser improves policy learning efficiency. Zero Shot, the robot with offline Laser, is able to open a door almost as fluidly as SAC trained on the joint space, and door opening is even smoother when we train SAC on the Laser action space. On the other hand, the untrained baseline cannot open the door. We performed experiments to test our hypothesis that Laser improves training on new task instances, where goals or physical parameters change. We find that SAC trained on the Laser action space outperforms SAC trained in the original action space, indicating knowledge transference. We also test online Laser using SAC. Similarly to offline Laser, we found that using online Laser improves sample efficiency when compared to the original action space, as can be seen by videos of rollouts with the same number of training steps. We traverse the latent space learned with offline Laser on Wipe. Different dimensions of the learned latent action space correspond to traversing different dimensions of the table surface, showing Laser learns an appropriate task manifold. In summary, we presented Laser, a method for action representation learning that improves the efficiency of reinforcement learning. More experiments in the paper.